Radioactive isotopes by me. We know that elements are identified and determined by their atomic number, or number of protons. But elements consist of neutrons as well. Neutrons help stabilize protons by cutting down the force that pulls protons apart. When an element loses or gains a neutron, the element does not change, but their atomic mass changes. These atoms are called isotopes. Take hydrogen for example. The one we're familiar with has one proton and no neutrons, but hydrogen has a natural occurring isotope called hydrogen-2 or deuterium that has one proton and one neutron. However, too many neutrons can destabilize a nucleus. An unstable isotope tries to become stable and thus starts to decay. These are called radioisotopes. Now back to the hydrogen example. Hydrogen has another isotope called hydrogen-3 or deuterium, a radioactive isotope with one proton and two neutrons. Reactions that involve or occur in radioisotopes are radioactive decay, nuclear fission, and nuclear fusion. Products of these reactions include energy or even the formation of new elements. Radioactive decay occurs when a radioactive isotope degrades to a lower energy element until stable. There are three types of radioactive decay: alpha, beta, and gamma radiation. During alpha radiation, the nucleus releases a helium nucleus, two protons and two neutrons, and can be stopped by a piece of paper. Beta radiation releases an electron or a positron and converts a neutron into a proton. This radiation can be stopped by aluminum sheet. Gamma waves are rays similar to X-rays but shorter. These waves can be stopped by lead or concrete. Radioactive isotopes have a specific set of half-life. Half-life is the amount of time it takes for half a sample to decay. Half-life ranges from a fraction of a second to 2 trillions of a year. Radioactive decay has a formula and is used to figure out how much radioactive material it remains over a period of time. Nuclear fission is the split of the atom's nucleus, forming elements of smaller nucleuses and particles. This usually happens in heavy radioactive isotopes. Under certain conditions, a nuclear fission reaction creates chain of reactions in generators. These reactions generate a large amount of energy. An example of a nuclear fission reaction involves firing a neutron to the radioisotope uranium-235 to create krypton, barium, and 3 neutrons. Nuclear fusion is when smaller atoms join to form larger elements. For example, the combination of deuterium and tritium in a fusion reaction is used to form helium and a neutron. Nuclear fission produces high heat, and high heat is used to produce fusion, and nuclear fusion is used to make nuclear energy. Other than using it for energy, radioisotopes are also used in medicine and geology. Radiology and nuclear imaging uses radioactive materials to study organ and bone. Radioactive tracers are very small amounts of radioisotopes added to body systems in order to study the system. Thallium-201 is a tracer to detect heart disease. The radioisotope interacts with body cells and radiates gamma rays. A computer reconstructs the 3D image based on the distribution of the gamma rays. Doctors can then see tumors, blockages, and defects in blood vessels. In geology, radioisotopes gives the ability to date fossils and ultimate age of Earth and figure out climates back then. Canada's initiatives to improve the quality of radioisotopes include improving medical radioisotope production, nuclear energy, nuclear waste, and research. Canada is the world's second largest producer of uranium, a radioisotope that is used for nuclear power. However, Canada generates a lot of radioactive waste. In November 2002, the Nuclear Fuel Waste Act required nuclear energy operations to reduce nuclear waste. The can-do design for a nuclear reactor has gone through changes to improve fuel efficiency, safe requirements, and reduce cost and construction time. This was completed in June 2013. Technological products that use radioactive isotopes are pacemakers, satellites, and submarines, smoke alarms, medical scanners and tracers, fuel rods, bombs, and energy. The benefits of radioactive isotopes are for safety and research, energy, and medical purposes. As concern to global warming increases, interest in nuclear power spikes. Nuclear power generates no greenhouse gases and materials available, and it's only needed in small amounts. However, radioactive isotopes has risks. It concerns moral, medical, and energy and environment concerns. The American government used nuclear weapons such as the atomic bomb against Japan to end World War II. Approximately 180,000 people died from heat, pressure, burns, and radiation sickness. Excessive amounts of radioactive materials can cause damage to the human body, for example, wrecking genetic material or DNA. This can go on for tens of thousands of years. Radioactive elements are produced in greater than normal amounts found in nature. As a result, land and water can be affected by radioactive contamination. Used fuel from power plants, for example, can be radioactive for a year. Currently, they are buried in concrete or lead bunkers underground. To finalize that, radioactive waste from nuclear power plants can remain unsafe for 20,000 years. Thanks for watching!